Hello and welcome to this class, and where we are introducing the measurement of color. So, if we have a colored solution or you have to do something to get a colored solution, and then we can monitor the color for say simple acid base titration, what we have discussed just now in our previous class, that if you have a colored solution and how we can detect that corresponding change in color only. So, this particular lambda, when we talk about the corresponding thing, is that suppose we have added a phenolphthalein to a solution and the color change is going from a pink to colorless situation, that we can determine visually by addition of that particular thing, that means that particular color. But if a solution can develop a color for a particular concentration of something which can be your ion like ferric ion. So, this ferric ion is there, we all know that is yellow to orange depending upon the concentration. So, it can be very light yellow only, which is very difficult to detect by only determination of that lambda value of that particular aqueous solution of Fe3 plus in solution only. So, what we do? We do something such that it can give you a strongly colored solution, which is very important. So, a strongly colored solution we can do. So, that colored solution, so we have to use some reagent, and that reagent can give rise to something which is basically nothing but a metal ion complex, and that metal ion complex is strongly colored and we get a new lambda max value having a characteristic E max value. So, what are these things? Now, we will see how characteristic these lambda max values and E max values for a colored solution, and how we can determine that with the help of a instrument. So, that is our basic idea for getting that thing. So, we just see that a metal complex can give rise to the corresponding color in solution, and as I told you, that is your FeCN2 plus will be forming there, and which is red in color and which is strong in color also. That means, what we are talking now is the corresponding colored intensity. So, it is red, but the information that it is only red is not sufficient. You should know also the colored intensity, how much red it is, which will depend on the species which is responsible for this absorption. So, we have to think of, we have to talk about, and we should know also how we can monitor the corresponding absorption pattern or absorption spectroscopy, what we will call it as an electronic absorption spectroscopy related to the species which is forming in solution as FeSCN2 plus. So, it is the first species what is forming in the solution from the reaction of his Fe3 plus with SCN minus. So, this aquated species what is there in our hand, as we all know, how we get that? We know the salt which is available in the laboratory having some n number of water molecules in it, that means water of crystallization you do not have to bother about, but when you quantify it, that how much iron we are dissolving by taking the weight of that ferric chloride in a solution which is slightly acidic with hydrochloric acid. So, this Fe3 plus which is forming over there is not a simple Fe3 plus only, but it will be the corresponding hexa-aquo species. So, the complex which is forming over there is coming directly from the dissolution of ferric chloride is your hexa-aquo Fe3 ion. So, hexa-aquo Fe3 ion, when it is reacting with thiocyanate, though different books and all these things are writing as only FeSCN2 plus, but is it only FeSCN2 plus? It is not that. what you see that this particular one, from the idea of the molecule itself, you have all the 6 positions, that means it is the octahedral species which is forming in our solution, and this octahedral species which is forming in the solution is such that when we write this as FeSCN 2 plus, that means charge is 2 plus, that means one of the charge is getting neutralized. So, one of the water molecule around this will be replaced by NCS, because it is ambidentate ligand, it can bind to the iron center through nitrogen and through sulfur, but here it is binding through nitrogen, and all other positions are occupied by OH2, OH2, OH2 and OH2. So, this is the species. So, that means this is the species FeSCN, and you have 5 other water molecules attached to it. So, due to the formation of these, since we are only considering the initial concentration of iron in the medium, and this initial concentration of iron in the medium, when it is reacting with only FeSCN 2 plus, it is forming a red colored complex, and if we can measure the corresponding lambda max and epsilon max value for this red solution, we can nicely determine any known as well as unknown concentration of iron in any solution. So, this particular one, that means your FeSCN 2 plus, which is red in color appearing. So, the complex does not add any red radiation to the solvent. It is interesting to know in this point is that the solution is red, we are seeing the red color. So, when we see the solution through our eyes, we see the solution as red colored, but we see something which we are not seeing something is that what it is absorbing. Since whatever we are talking all these cases, that means this lambda max, we will be talking now in terms of the corresponding radiation absorption, because this is the absorption spectra what we will get. So, electronic absorption. So, what is absorbing? So, the red colored solution does not mean that it is absorbing red wavelength or the red radiation. So, what is that radiation? So, what should be its lambda value? So, if I ask you that what should be the lambda value for the corresponding red solution, you have to think for a while. So, the red solution for this iron thiocyanate complex in solution has a characteristic lambda max value due to the corresponding green region of the spectrum. So, when it absorbs in the green region, it transmits the red component, that is why your solution is red in color. So, we should know now what should be the corresponding lambda value or the lambda max value for this green region of the electronic spectrum. So, we will be using some radiation starting from your visible range, say 350 nanometer to 750 nanometer say. For this analysis, since color is responsible, so any colorimeter can also be useful, and we can consider it as a colorimetric analysis and should be complementary to that of the solutions. That means, what color it is absorbing, when green is absorbed, we see the corresponding complementary color as red for this particular solution. So, if we can have for this the whole range, so it is a textbook stuff again, and from that particular textbook what we are discussing all the day, that is your book of Skoog, and you see the corresponding thing, that this is a typical chart where we see that you have learned from your early years of learning that what we have, that violet, indigo, blue, this range to red, we all know this is the Vibgyor range. So, Vibgyor range is starting from 400 nanometer to 750 nanometer, and if we color wise, if we divide it into blue, green, yellow and orange and red, we get this. So, what we see that for this particular solution of iron thiocyanate is a typical example which is red to purple in color. So, if it is red to purple in color, its corresponding color which is being absorbed, the lambda value which is getting absorbed for this particular solution, which will be red in color, is from blue green to green. But in terms of the corresponding lambda value, we see that the corresponding absorption will be in the range of say 500 to 560 or 580 nanometer. So, this is the corresponding lambda max value. So, what we see, that we see only the red color, but visually what we are trying to detect is that, so once you have the red, because these are all complementary color, again the same color sequence is there, but only thing that your now violet is starting from here. So, again the whole range violet to red is violet, blue, blue green, green blue, and then again going back to yellow green, yellow, orange and red. So, it is only from here you have to write the same sequence where you are starting here. So, instead of starting violet to red from here, you have to highlight here, and again you go back and go up and come over here as a red. So, the complementary color very quickly you can write, and the ranges are also not very much. Some of the ranges are big enough, but some of them you see this is 35 nanometer broad, this is also 45 nanometer. So, this 30 to 50 nanometer of this broadness, only thing the red range which is quite a broad range, which is only 100 nanometer. So, this is the broadest range which is the red range, that particular absorption. So, if the red is absorbed, and we know large number of solutions what we can get in solution from the dissolution of the metal ion in solution also, which are green blue in color. So, once your solution, we know that how FeCN SCN2 plus is forming. So, this is giving you the red color. So, this is giving you the red color, means you have the corresponding green to yellow green in absorption, green to yellow green in absorption. That is why you know the lambda now. So, lambda will be in the range of 580 nanometer. So, 580 nanometer we get. So, if we have some unknown iron solution, so what will you do now? Is in your hand now, all the informations are there, that you add the thiocyanate will react it with it, and if this is the thing, your stoichiometry is also should be controlled, it should be 1:1, and when this stoichiometry is controlled, you corresponding thing you generate, this particular species you generate in solution, and you generate the red solution, you determine that whether you have the corresponding absorption at 580 nanometer or not. You determine that absorption and how to detect this particular one, that means how much absorption can take place at that particular point, is very simple to know, is now the corresponding lambda max value. That means, how you correlate this lambda value to any concentration. And what is that concentration? We are looking for a concentration of Fe3 plus. So, that is our next goal to establish, that how we establish, once we know the corresponding lambda value, the corresponding concentration. So, there will be some species, and we just introduce something to you now, is a name of a molecule, because it is well known to everybody nowadays, because it is a very good food coloring agent and is tetraagine. So, agine is, we all know that the agine and azo is all are related to the nitrogen. So, is the yellow azo dye. Just now we are talking about something as the methyl orange, and I told you that your methyl orange, which has a corresponding NN double bond or the azo function. So, if we have a azo function to any organic molecule which is giving rise to the colored, and which is the only part of the big molecule, the whole molecule, which is known as a corresponding chromophore to that particular molecule, because all we know that in most of these cases what is giving rise to us is that this particular chromophore, the azo chromophore, can give rise to a corresponding color absorption in the lambda value, that means its lambda max in the visible range. So, what we will be looking for, why azo is so important is not like that, it is that we are looking for something where we have the nitrogen bonded by a multiple bond, that means we have one sigma bond and another pi bond. So, the electronic energy what is being absorbed can change the corresponding orientation of these electronic distributions basically, because initially what we consider that when bond is forming and this sigma bond is forming, that means it has the sigma orbitals have some electrons and then pi bond is also there. But if we have some electronic transition and we can promote, it can be a very short lived transitions for a while only. So, if we are able to promote those electrons only which are not so tightly bound like that of our sigma bonds, because if there is one carbon in this side and another carbon on this side, so this carbon nitrogen bond is also attached by a sigma bond. So, only available bond over here is your pi bond, and also we should look at the corresponding available lone pair of electrons on this nitrogen. So, these electrons basically, that means the sigma electrons and the non-bonding electrons are available which can take part in these electronic transitions. So, this can be a very useful chromophore because it can absorb the radiation. So, electronic radiation in the form of H nu it can absorb, and due to that absorption we see the corresponding color for the presence of this azo group. So, if we define this as a lemon yellow, so it is not a typical yellow like other yellow what we have seen for other azo compound which have been used in our previous class for your methyl orange discourse. So, when we are discussing about the indicator of methyl orange, there also the azo function is there, but the other part of the molecule is different in this particular case, and which is also a very good and safe molecule for use in our food material. So, you see though it is a very big organic molecule, but still it is safe, it is not harmful for our body. We can degrade this molecule very nicely and we can pass from our body also, it will not accumulate in our body. So, that is why it is a approved coloring agent, but this particular color is for the yellow color and which is a lemon yellow color. So, it is a different type of yellow color which is lemon yellow color. So, you see you have CC double bond, CN double bond, but everything is getting modulated by this particular azo function. So, these are azo dyes. So, azo dyes and all these things are very useful starting from your textile industry to the food industry. Then another example of azo dye is on the similar line which can also be used for detection of something as a coloring matter is your sunset yellow is another name, is a petroleum derived azo dye, because the petrochemicals we all know these are naturally available chemicals what we get from the petroleum products and is basically dependent on maximum absorption at about 480 nanometers. So, you see now is the lambda max is leveled. So, the dye is leveled with the corresponding lambda max value of 480 nanometer in some acidic pH value. So, earlier whatever we have seen in case of your methyl orange and methyl lead indicator, you can have two forms because you go for the corresponding deprotonation of the phenol part, but here we do not have any phenol part in these molecules. So, you do not have any form like HIN and IN minus. So, this is the only form. Only thing is that you can have at a very high pH value, there are certain positions like these nitrogens having lone pair of electrons, this nitrogen having lone pair of electrons, and those sites can be protonated. So, the protonated can be there, protonation can be there on those nitrogens similar to that of your sunset yellow, where you can still have a naphthal unit. So, this is the naphthalene part and this OH group is also there. So, it has a maximum strong absorption at a pH 1 because you have to protonate this particular part at pH 1. So, this is basically another approved dye for food coloration and which is again dependent on the azo function. So, we defined chromophore and how we utilize this particular chromophore to detect a particular color in this particular fashion. So, this is a very big list, but if you just simply look at is a very exhaustive list, and why we are talking about this particular list is that what we can have, that is we have not given something what we have discussed just now is that determination of this iron. So, this particular iron by some other reagent, because if you want to modulate the change, but again you see the determination of iron by some other reagent. So, reagents are different. Earlier we are using thiocyanate to get some particular type of complex with a minimum stoichiometry of 1:1 and the corresponding intensity is very high and is not a simple color change for the corresponding transition based on the iron as the corresponding Fe site, because is all these things are written as the corresponding metal center, because the element to detect, but not in this particular form. These are all in the corresponding state as the corresponding either ferric state or the ferrous state. So, when this solution is red colored, so what is the color which is formed, and we should also label it with the corresponding lambda max, that the solution is red, but it is absorbing in the green and the yellow green range, which is in 512 to 562 nanometer, and which will be useful like that of your thiocyanate for the determination of the corresponding iron in the solution. Now, we will take another example, very simple example for the first one. So, if we try to detect aluminum also, which is not a transition metal ion, because most of these transition metal ions we all know they are colored, they also impart some other coloration to the solution when it reacts with the reagent. And a very specific reagent we call it as 8-hydroxyquinoline. So, what is that reagent? So, we are introducing something which is as a reagent and it has some other purpose also. Now, we consider it as a coloring reagent, which is the name what we have written is the corresponding name is your 8-hydroxyquinoline. So, this is the 8th position of the quinoline, the whole other is the quinoline, and this is the 8th position of the hydroxy ion. So, is the coloring agent for aluminum. The detection of aluminum, it can be metallic aluminum, but always remember that if you are going to detect aluminum metal or the aluminum sheet, so this aluminum you have to take into the solution as aluminum 3 plus. So, this is known as pretreatment, and this pretreatment from aluminum sheet or aluminum wire or aluminum rod, whatever it is. So, pretreatment is giving rise to Al3 plus in solution, or in other way, if once you know the procedure, you can handle say some aluminum based alum. We all know that the double salt alum is there, where aluminum is present along with any other corresponding cations like sodium as well as the potassium. So, the sodium and potassium based alum will give you something where we find that this is there. So, is directly you can get aluminum in the solution by dissolution only. So, solution to make only by addition of water, but in this particular case to go for this aluminum sheet or wire, you have to go for some treatment with acid. So, acid digestion treatment will be there such that aluminum will be oxidized to aluminum 3 plus. Now, we see some coloring agent we are adding. So, depending upon the level of concentration, if the concentration is very small in a large volume of water, so volume of the medium is important. If the medium is very high, that means the volume of the medium is very high and the amount of iron 3 plus in the solution is less, what will you get over there? That means, if we get this particular one with some slightly alkaline medium, slightly alkaline medium. Why slightly alkaline medium? Because you have to take out this as H plus and you have a charge on O minus. So, this particular one, this reagent is nothing but a ligand. In a coordination chemistry, what we study as a ligand. So, we will be exploiting that particular reaction of a metal ion and the ligand. But whatever we have studied in our school level also, that M is reacting with L, giving rise to the corresponding formation of Ml, as we have seen in the different chemical equilibrium also. But here this particular one is for the complex equilibrium for the formation of Ml from M plus L. But if we say that why it is not forming MLN, what should be the value of N for this particular reaction, which was also true for your iron thiocyanate. So, if this ligand is there, and we should also know, because once we know this and once we know the formula of this MLN, because the stoichiometry is important, whether the metal ion Al3 plus is reacting with that particular ligand in a stoichiometry of 1:1 or 1:2 or 1:3. So, this binding of this Al3 plus by this particular ligand through nitrogen and oxygen will give rise to a typical octahedral complex, where we all very easily draw this, and through this nitrogen and through this oxygen. So, one of this particular binding is like this. So, this is one such ligand. So, this is 1L is binding to this your aluminum center. Then the second one will bind two other positions and the third one will be other position. So, your N value will be equal to 3, and we write this as the Al, oxine as the OX. If we abbreviate this oxine, this is the name of this is oxine, 8-hydroxyquinoline is nothing but the oxine. So, the formula of the compound is AlOX whole 3, which is yellow in color, and we know now the lambda value for this particular yellow solution or the yellow coloration. So, we will be able to detect the aluminum 3 plus solution, which is colorless in the solution medium, and if the concentration of this solution is that metal ion or the aluminum ion is very less, your color will be more and more faint. So, by the addition of this particular reagent, which is oxine, and by knowing the corresponding lambda max value, this we are not considering right now, but what we will be seeing that we will be able to detect this lambda, and the sharp detection of this lambda at a particular value where you have a maximum absorption, that means the maximum color absorption can take place at this particular wavelength value, which is yellow for this color, we can detect by using a spectrophotometer. So, this coloration for 8-hydroxyquinoline, which is yellow, so you see it is in the range of say which is very far from the corresponding visible range, and which is strongly yellow only at 295 nanometer. So, uses close to 300 nanometer basically. So, but the instrument can detect it, but it is very difficult to detect that through our naked eyes. Okay. Similarly, all these things, all these species, the basic idea what we are trying to say you is that if you have iron, is don't think that this iron is binding with this particular ligand. 1,10-phenanthroline is also known as orthophenanthroline, and this orthophenanthroline is like that of our oxine. This 8-hydroxyquinoline is also binding with this. So, this is also with this 8-hydroxyquinoline. So, this phenanthroline is also binding to say ferrous ion Fe2 plus nicely. So, forming the red and is have a very high intensity. So, we will be able to detect that particular ferrous ion solution in the medium by the addition of 1,10-phenanthroline, and if the corresponding epsilon value is very high, that means your intensity is very high, we will find that you can go to detect a very low concentration of this iron solution in the medium. Similarly, this is another reagent which is the trait name is known as the ferrogene. So, ferrogene can also dig that particular detection, but these two are very important, that if we have anions also, not only the metal ions, but also the anions like phosphorus, like sulfur, giving rise to the corresponding anions phosphate and sulfite or sulfate. So, these can also be detected by some reagent. So, this molybdate, and when we go the hydrogen we detect. So, molybdenum blue we basically form in the medium, and that molybdenum blue formation will be assisted by the formation of the phosphate ion, because the molybdate MoO4 is very much similar to that of your phosphate, and this phosphate will be trapped by this molybdate, and a characteristic blue coloration is forming over there, and that blue coloration has a lambda max at 830 nanometer. You see, if we consider our visible range finishes at 750 or 800 nanometer, but this particular can show, because the tail what we will be discussing afterwards in our next class, that how broad your absorption spectrum is, that we will be talking something with that this broad absorption spectrum, and that broad absorption spectrum, the tail is coming in the visible range basically, but it is going upward to a longer range where we consider that particular range as the near infrared region. In the NIR region, so the your wavelength range for this one is 830. So, the spectrophotometer can nicely detect that absorption, where a amount of light will be absorbed by the medium and the amount of light reaching the detector will be detected over there. So, this and that also. Then another example is the corresponding zinc, which is not colored, which is a colorless solution in the medium, and dithizone is again nitrogen and sulfur based reagent. So, these are all very good ligands. So, these ligands whatever we are used for that, which can bind the zinc center, that can also be detected or used for this particular lead also. You see that common reagent which is the lead and which is also for the zinc, and you see in both these two cases the color is pink, and here it is also pink. But sometimes we will find that the same reagent can give rise to two different colors for one metal ion and the other metal ion. So, the same reagent we can use for that detection even in a mixture. But in this particular case, since the color is same and the wavelength range, if for the pink, if the color range or the wavelength range is in the close by, we cannot detect a particular type of mixture. Okay. So, this manganese, once you see the reagent from this particular chart, you should all be able to read this thing. That means the reagent is pyridate. Pyridate is not binding to this manganese as the corresponding manganese ion. So, this manganese ion is there, and is the pyridate is be oxidizing this manganese to permanganate ion. So, that is why this on the right hand side what is written over as the color is the purple, and this purple color is nothing but your formation of the permanganate ion, which will be absorbing at 520 nanometer. So, the next day we will consider how in a solution you have permanganate ion, or coming from the chromium the dichromate ion, how we can detect by the help of a corresponding spectrometer visually by the use of absorption spectrophotometry. Okay. Thank you very much.